Let's take some time to discuss a fun Tinkerpop gremlin concept called bulking. So what is bulking and how does it work? Bulking is a built-in performance optimization that basically boils down to this. If you have multiple identical traversors at the same point in the traversal, then they can be merged into a single traversor that knows how many of itself it represents. This can have a profound influence on the performance of your traversal in cases where you have a lot of duplicate traversors. So don't worry if that didn't quite sink in yet. This sort of thing tends to click when you have a picture. So let's imagine that we have a traversor that is propagating through this lattice graph. As you can see on the left, these traversors start to build up as they propagate. Each of these traversors has a little memory footprint and needs to be processed individually at each step. But the folks who built Gremlin are smarter than that. They recognize that rather than having duplicate traversors flowing through the system, hogging up memory, they could simply have one instance of the traversor that knows how many other traversors it represents. And that's what we're going to see here. The bottom right, you see that there's a single traversor that actually represents 20 clones or copies or instances of itself. Now this all happens automatically under the hood, so in most cases you don't need to worry about it. You can simply sit back and enjoy the performance boost. Gremlin will identify traversors that can be bulked and do it on the fly. Gremlin will bulk traversors if they meet at an intersecting path and the path history is not used later in the traversal. So if you remember from a previous section, we discussed that path history can be quite expensive, and this is partly why. It prevents bulking. Here's the list of steps that should be avoided in order to realize the performance boost that bulking provides. And you'll notice that each of these steps requires some path history in order to operate. Let's take a look at an example to see just how bulking can influence the performance characteristics of a given traversal. These two traversals are very similar in that they both do a breadth-first traversal across the graph, but the first traversal is saving the simple path history along the way, which as we now know will prevent bulking. Here's some profile step data on each of these traversals. The element counts for each are identical, but look at the traversor count column. Wow! In the last row, you can see that the bulking traversal was able to capture all 20 of the remaining active traversors in just 2 actual traversors. So even in a tiny little example like this, you can see the impact that bulking can have on the memory and computation needed to complete our traversal. And things continue to get more exciting as you scale this idea. Here we have a table that shows the traversal execution time for a non-bulking and bulking traversal. The important thing to notice here is the relative difference between the last 2 columns. This highlights the incredible performance boost you can achieve from bulking. Some closing thoughts. As we covered earlier, this all happens automatically. The important thing to be aware of here is that bulking is happening under the hood. This will help you reason about the performance of your traversals and also provide some understanding of why certain steps seem to introduce such a large performance hit, while others perform so well that you're afraid it might be too good to be true.